This is the second part of my video on how to write a Matlab code to read data from IEEE Common Data Format. In the first video, we'll learn how to read data from an input file in Common Data Format. Also, we got the sparsity pattern plot of Y-bus. So in this video, we will solve power flow analysis by using Newton-Raphson Method for iteration. Before explaining the computational method, let us briefly talk about the type of buses, like slack or reference bus, generator or PV bus, load or PQ bus. There is one slack bus in conventional power flow analysis, and is selected as the angular reference for all the buses. So the angle for this bus is usually selected as 0. Magnitude of the voltage is known, and the uncontrolled values are real and reactive power. So it is useful to balance the active and reactive power in a system while performing load flow studies. In PV buses, generators are connected. So the power generation and voltage are controlled through a prime mover and the generator excitation. So we need to find the reactive power and the unknown component angle delta. The load bus, which is also called as PQ bus, no generators are connected. So the aim is to find the bus voltage magnitude and its angle. So now let's move to the computational method. In the first part of this video, we obtained the bus admittance matrix and the sparsity pattern plot of Y-bus. So we will use all that information to analyze and calculate the power flow problem. Okay, let's go through code. We were at line 160. Base power is initialized to 100 as input. Here for loop is created to determine each columns of the system. For example, column 1 to 4 will give us the number of buses. Column 25 to 26 determine the type of buses. As I mentioned in the first video, when the integer type is equal to 3, that represents a slack bus. 2 represents PV bus and 0 represents PQ bus. Similarly, columns 28 to 33 shows the specified voltage or final voltage per unit, and so on. Since all these columns were given as character array or string scalar, so I used str to num to change them into numeric matrix. For further information about each column, you can look at IEEE Common Data Format. Here in bus data cards, you can notice the data of each column. In this code, I didn't include some of these columns like shunt conductance and shunt susceptance. So you can include these parameters by using similar way. Here we just specified the data of each columns for all the number of buses. Then those data are classified separately to its own type, like voltage, P generator, Q generator, P load, Q load, Q minimum, Q maximum, slack bus, PV bus, PQ bus, and so on. After finding all these parameters such as bus voltage, type of buses, angle, powers, and so on, we can apply Newton-Raphson method to calculate the power flow problems. So to find the unknown parameters, we need iterative procedures to find these unknowns, and then calculate the mismatch powers. With each iteration, the mismatch power will reduce and load flow will be converged. When the mismatch of each passes become less than a tolerance number, which is very small positive number like 0.0001 or 0.001 like here. Actually, Newton-Raphson method is one of the best numerical algorithm to solve nonlinear equations for such a large data. Pi will give us the real power and Qi will give us the reactive power. In Newton-Raphson method, we have to bring the equation to the form of f x1, x2, xn, where x1, x2, x3, xn are the unknown variables to be computed. If we have n PV and n PQ buses, the unknown variable that must be calculated are the angle of the complex voltage at bus I for all the PV and PQ buses, and the magnitude voltage at bus I for all PQ buses. Here in the following, there are n and m unknown variables that will be calculated, and the iteration will stop when delta P and delta Q are within the tolerance values. At each iteration, the mismatch power delta Pi and delta Qi reduces and the power flow will be converged when the mismatch of all buses become less than tolerance values. Next, we need to calculate the elements of Jacobian matrix. We just specify them into submatrix of J1, J2, J3, and J4. The size of Jacobian matrix is n plus np plus 1 multiplied with n plus np plus 1. By utilizing the real and reactive power equation, we can obtain the submatrices of Jacobian matrix J11, J12, J21, and J22. For example, for IEEE 14 bus system, the number of PV bus equaled 4 and the number of PQ is 9, so the size of Jacobian matrix is equal to 22 by 22. After the Jacobian matrix is calculated, here I just write the unknown parameters need to be calculated. Now let's call our function and see the result. The name of our function is asa underscore pro CDF path or file name. In command window, write asa underscore pro. Inside bracket, write your input file. Let's call first IEEE 14 CDF.txt. Click enter. Here in the command window, you can notice the updated values of the magnitude voltage and angles. First bus was a slack bus that the magnitude voltage is 1.06 and the angle is 0. Second and third bus was a PV bus, so we also need to calculate the reactive power for them. Fourth and fifth bus was PQ bus. As you can see, the updated values of magnitude voltage and angles. Similarly for all the buses. Here you can see the dimensions of Jacobian matrix, which is 22 by 22, the number of iteration, that is 7, and also the elapsed time t equal to 0.0209 seconds. If we call IEEE 30 bus system, the number of iteration increases as well as the elapsed time. As the number of bus increases, the number of iteration and elapsed time increases as well. And because large amount of data will be calculated to convert the system.